Okay, so this is an example that illustrates strong induction. I think it illustrates it pretty well. I've been struggling a lot with it, and after a few days of kind of banging my head against this concept, I feel like I finally got it. And it doesn't seem to be as hard as the textbook makes it out to be. So I'd make a video explaining my understanding of it, mostly just for my own my own betterment, just to make sure that I do in fact understand it, so I can explain it to other people potentially. We've been watching too much Ali Abdullah lately, but yeah. Okay, so this example says a chocolate bar consists of unit squares arranged in an n times n rectangular grid. You may split the bar into individual unit squares by breaking along the lines. What is the number of breaks required? So this is pretty generic advice that I feel like everybody in math or computer science has received, but it's always great to do a diagram. I don't really follow my own advice often, but I should more. So I'm going to go ahead and write a diagram of like a chocolate bar, I guess, a square chocolate bar, and maybe do different shapes to see kind of if I can guess what function models this type of behavior, because it's hard to kind of just think of what this might be without a tangible example. But it's when I did this problem initially, I was surprised about how quickly the answer came to me when I just was able to write it out and think of it as an isolated example. It's really easy, especially with proofs, to just think of the generic solution. The actual end goal of the proof is to prove it generically. But for isolated examples like this 4x4 chocolate bar, you get a better sense of actually how it behaves than if you were to think about what if an n by n, some obscure, abstract chocolate bar that doesn't actually exist, because we don't think in terms of n and m. We think in terms of a 4x4 or a 2x8 or whatever, and then how it actually breaks down. And that's true not only for this example, but for a bunch of other math examples. So let's just do this one. So if I were to break this bar apart, I would start with here, and then I'd break this one and then this one. So I have 4 lines of chocolate as it were, individual, and I've done 3 breaks so far, and then I'd break it along each of these lines. So I'd break that one, and break that one. And so what are the total breaks? Well, I break this one. I should probably make that a straight line. I break this one, break this, so that's 3. And then I break this one, 1, 2, 3. So far we're at 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. That's 15 breaks in total. Okay, well, so far, I'm still on that mode. So number of breaks equals 15. Okay, so I have a few ideas about what might this be, but it's not good to do just an n of 1 study, as it were. Let's try a different bar and see if we get kind of similar results. So I'll do a 3 by 5. Break this up. Okay. Now, as I'm writing this, I'm thinking, why am I doing an orange chocolate bar? But maybe it's one of those Quality Street ones. Okay, so orange chocolate bar, and we need to break it up using a blue break things. So let's break it here. We get 1. We get 2. Okay, so 2 breaks. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, good to know. So the number of breaks is 14. Now, in the actual example, when I was doing this initially, I did like 3 other ones because my head is relatively large, relatively thick, I should say. And so it took me a while to find the pattern. I'll say 14. But I'm going to cut to the chase here. And once you do enough problems, you'll find out that generally what happens, so here in this case we had this was 4, and this was 4, this was 5, this was 3. And generally what happens is we do the length times the width, and then it's minus 1. So for here, it was 4 times 4, which is 16, minus 1, which is, of course, 15. And then here it's 5 times 3, which is 15, minus 1, which equals 14. Because these things aren't really equal, but you get the idea. Let me just put a minus 1 here. Minus 1 equals. Okay, so, and if it took you if you tried this problem before I did the explanation and it took you a while to get here, that's totally fine. Just do as many examples as you can until you find the thread, until you find kind of this function that you're trying to prove. And so finally we get something like n times m minus 1 equals the number of breaks. Right? Okay, so that's great. And honestly, if you're explaining this to a person, that's all you had to do. Just give a few examples and then you're done. But we're doing math proofs. So I have to do a rigorous proof of this, right? Just these examples won't do. So now we actually have to use strong induction to prove this. So proof. And so I'm just going to lay out the kind of basic idea of strong induction here, now that we have an idea of what we want to prove, and then we'll actually apply those principles. So it'd be like laying out a recipe and then actually making the bread or whatever. And so what we need to do is our first step is the basis step. Okay, so this basis step, what you want to do is you want to prove it's similar to the basis step for ordinary induction in that you want to prove a few cases. If, for example, if we had an infinite ladder, right, and we needed to climb up this ladder, right, and each of these were steps, the basis would be the first rung, right? We'd say, okay, well, for one isolated case, oftentimes it's like an n of 0, right? It's the very basic thing that you need to prove. The first step, we need to get on the rung, and then we need to prove that we can get to the different rungs of the ladder, right? We can get from one to the other. But first we need to get on the rung. So what do I mean by that? So if P is our proposition, the basis is often P of 0. Generally I'll say P of A, P of B, P of C. The point is they're isolated examples. We aren't going, from K to K plus 1. They're isolated examples that prove our proposition is true in these isolated examples. It doesn't prove the whole thing, right? That's why we need strong induction. But it gets us on the rung of the ladder. And then in the induction step, we prove that we can get, now that we're on the ladder, we can go from one rung to the other and then, go up infinitely if we use this metaphor. Okay, so hopefully that makes a little bit of sense. Let's actually do an example, maybe become more clear. So for basis, what we need to do for here, we need to show that the really base case, which is when n and m equal 1. So that's when our chocolate bar is literally only 1 unit, right? We can't break it up anymore. Does our hypothesis, this idea that n times n minus 1 is the number of breaks, does it hold? Let's see. Well, we get 1 times 1 minus 1, which equals 0, and that checks out because we can't break this anymore. It's 1 unit, right? So that's done. And oftentimes for strong induction, you need to do more than one basis. And it depends on the proof that you're doing. For this, we don't need more than one basis. One is enough. And so we'll move on to our induction hypothesis. So we just need to state our induction hypothesis. And this is where it differs from ordinary induction. Finally, we're getting to the meat of what strong induction is. And so here's what it is. We're going to say from 1, actually what we can do is we go Ni times Mi minus 1 equals the number of breaks. Maybe it'd be better practice to put an assume before this to show. So say assume Ni Mi minus 1 equals the number of breaks. Let me just move this a little bit closer. I have a little bit more room. And then we can say 1 greater than or equal to I, and this should be, this should be J. I greater than or equal to some upper limit K. That looks like an H, K. And the same thing for J. The whole point of having them different is so that it's just showing that it doesn't have to be a square, right? I and J can be different. Say I is 3 and J can be 4. They can be the same if they want to be, or if that's the example. But we have I and J there, some arbitrary thing that is below our limit. And so we're assuming that this is true. We're assuming here that our theory is true. And we need to prove that the next step follows from this assumption, right? And so that's where our induction step comes in. So we're assuming that this thing is true, and then we need to say, okay, well, if we have K plus 1, right, this next step, is that true? So for the latter example, right, what we've just done, we said, okay, well, we've gotten on the first rung of the ladder. We've proved that the basis is true. Okay, so far so good. Now we need to prove that we can get, no matter which rung we're on, we need to be able to get from one rung to another. And that's what this induction step is saying, right? And so what we're saying with the induction hypothesis is we're saying, assume that we've gotten to some rung in the ladder. It doesn't matter what it is, right? And so that's what this is. We're saying, assuming we're on some rung of the ladder, which can we get to the next one, right? And so that's exactly what we do. So I'm going to say the induction step now. Induction. Okay. And what's the induction step? Well, we need to prove that n of k plus 1, so notice it's outside of this range, times m of, there should be m of k plus 1 minus 1 equals the number of breaks. Let me get a room here. All right? So how do we do that? Well, let's just do some, good old-fashioned reasoning. So if we break an n k plus 1 times m k plus 1 bar into two different pieces, we'll get two new bars, basically, right? We break a chocolate bar, if you just think about it in your mind's eye, and we break it in half, or, doesn't have to be half necessarily, we just break it into two pieces, we get two new bars, and say we break it along the n axis, then we'll have two smaller bars. One's, say, n1 times m, the other one is n2 times m. So let me illustrate that with an example. It can be kind of hard to talk about it without a visual example. So say we'll have this bar here, right? Oh, a bit of a glitch there. Okay, we have this bar here, and then we break it into two pieces. Let's see actually how big is this. This is 5, so I'll do a 3. That's by 6. Yeah, awesome. And so that's one of the bar pieces. So this is this is by 7. Let me just put the dimensions here. This is 7, and this one's 5. Okay, so I've broken this. This is now 3, and then of course we have a 2, and then of course we still have 7, right? Because we didn't break it along the horizontal. And this is a pretty rough drawing, but you get the idea. Okay, 2, and here we got 7. Okay, and this is 7 as well. Okay, so what did we do here? Let's generalize what we just did here. Well, if we have an n times n bar, and we break it, then the product is sum n1 times m and some other bar n2 times m, right? Why is this important? Well, notice this. n2 plus n1 equals n. And by the nature of the problem, n1 and n2, oops, I did 2 n2s, n1 and n2 are less than n. What does this tell us? Well, here we can use our strong induction. Why? Well, remember what our hypothesis was. Our hypothesis was that some ni, right, which is less than k plus 1. Why is it less than k plus 1? Well, we said it's less than k plus 1 right here, right? So some ni that's less than nk plus 1. And we're assuming that for that bar, that this is true, right? So what we did here is when we broke it, now we have 2 bars, n1 plus m, n1 plus m, and then 2 plus m, that we're both assuming follow this assumption. You're saying, well, we haven't proved that assumption yet. I know, that's the whole point of strong induction, is we're assuming that's the case, and we're showing that if we assume that, then we get a proof that proves that the next step is true. Okay? All right, so we're assuming that n1 times n and n2 times n both follow this principle. So what we can do now is we'll say, okay, we'll say the number of breaks for nk plus 1 times nk plus 1 equals, I'll just put number sign, but number of breaks for n1 times m plus 2 times m. And remember, this n1 and n2, these are the 2 new bars that we did when we broke our bar, right? And so now what we can do is we can take these 2 and we can actually sub in our formula, because we're assuming that we can use that formula by the induction hypothesis. So I'll say by strong induction, or I'll maybe just say by our induction hypothesis, then we can say the number of breaks. My K's have been weak today. Number of breaks equals n1, I won't use the multiplication sign, I'll just do here, minus 1. Oh, and one thing I forgot up here, which is pretty vital. Is that this isn't necessarily true. Why? Well, we just broke it. To get to these 2 bars, we need to break it. We need to break it once. So I just need to add a plus 1 here. My bad. Hopefully that makes sense, right? To break it into 2 bars, we need to break it in half. and then use the 2 bars. So we need to include that break that we did. All right, sorry about that. Okay, so moving on. So now we can say, we'll sub the formula that we assume for N1 and for N2. Let's put these in brackets. This is here, and we can't forget that +1. Now what I'm going to do is I'm just going to do some very simple algebra to bring these 2 terms together, right? So this -1 and this +1 cancel out, so we're left with a -1. And then we get, so N1 times M plus N2 times N. I see some potential for simplification, so we're factoring here, and then -1. So I'm going to take the M out, then we get N1 plus N2 -1. Wow, now this is pretty awesome, because what do we have here? Well, earlier we said that N1 plus N2 equals Nk plus 1. So that tells us that M times Nk plus 1, and remember, I kind of just dropped the k plus 1 without even telling you, but we're assuming that this is Mk plus 1 as well, times Nk plus 1 minus 1 equals what? The number of breaks. And this is exactly what we wanted, right? This formula right here, which we derived from our previous assumptions, is the formula we're looking for. Is a formula we're trying to prove. And so we can actually just say, we can just end our proof. This is true by strong induction. So what did we do? Well, using our ladder example, we got on the rung. How did we get on the rung? By our basis. We said, okay, well, at least one time when N and M are 1, at least one time it's true. That doesn't do too much for us, but it gets us on the ladder, as it were, our proverbial ladder. It gets us here. But you're saying, well, there's an infinite number of rungs. That doesn't really do anything. Yeah, it doesn't. But if we can prove that for every rung, we can get up to the next one, then that would help us, right? Like, yeah, okay. Well, we're on the ladder. All we need to prove now is we need to get to the next one, and the next one, and the next one. And that's what induction does. We're saying, assume that we've climbed to a certain point. And that's what, again, using this ladder analogy, that's what this is. Assume that we've climbed to a certain point. Well, then, if we can get to the next rung, then for any rung on the ladder, we can get to the next one, right? Because we're just doing a general rung, this rung K, rung number K. If we can get to K plus 1, then that means we can climb all the way to infinity, right? Using this analogy. It's like, okay, cool. All we need to do is prove that, and that's exactly what we did. We proved that we can get to this next step. Hopefully that makes sense. Induction is a hard thing to wrap your mind around of. I just thought I'd make this video, just do lots of examples if you're still stuck. Thanks, guys.